Okay, so we need to talk a bit more now about what the photon model really means. We introduced sort of the necessity for it with the photoelectric effect, but there are more consequences to treating light as this particle or photon concept than just that. I'm going to do this in two parts. This part is going to be sort of the lecture part, the descriptive part, and then the calculation problems will be a separate one to sort of keep the time down. And so we're going to cover a little bit of chapter 25.6, which is sort of a contrast to the wave model when the waves were introduced, and then back to chapter 28 with section 28.3 that sort of expands on that. Oops, wrong thing. Okay, so the important core of what we're talking about here is that we've now learned two different experiments that give two different results, basically. That light is a wave from things like diffraction, interference, and light is a particle from things like the photoelectric effect. And there's some others that we're going to talk about as well that sort of hint at light behaving like a particle. And so we need to figure out sort of the full properties of that particle-like nature of light. The first thing is understanding the difference between the wave model and the photon model. And the easiest way to do that is these two pictures right here. So this set of pictures is sort of what you would expect if light was a wave and you just reduce the amount of light in the picture. So maybe this first picture is, a typical camera photo. It's open for, a couple milliseconds, the shutter. The next one, maybe the camera is open for just a much smaller time, say a fraction of a millisecond. And then this last one, it's open for even less time. And as you notice, the picture stays the same, but you just get less and less overall light. Like everything is just a little bit darker. That's exactly how a wave would behave, right? There's light everywhere because the wave goes everywhere, but you just get less intensity. In contrast, this set of pictures over here is what would happen if you reduced the intensity of a photograph a lot more. And that's sort of the particle model. So the last picture, right, is still correct, right? It's the correctly exposed photograph. But as you reduce the light intensity more and more and more, instead of seeing the whole picture just get a little bit darker, you start only seeing light in certain locations, right? Like for example, right, there's a little dot right there. That is representing like a single photon of light. And basically every point on that picture is either as bright as it's ever going to be if the photon gets there, or it's completely black if the photon hasn't. And that's a very different, right? These two pictures are very, very different from each other. They're very different predictions. And so we have to kind of understand sort of the difference between the wave model and the photon model before we can really understand what the photon model implies. And this contrast is the important result of that. To be accurate, though, these are both like correct, but they're at different situations, right? These are very low light levels, and these are higher light levels, and so it's a question of degrees, right? If these were like milliseconds or less, these might be micro or nanoseconds, even less light. So you can actually see the photon part of the model. Right. So there are three things that are important to know about the photon model. The first is a really nice thing, right? Light is light. If it traveled at the speed of light as a wave, it travels at the speed of light as a photon. That does not change, right? That's something that's consistent between both models. The second is the result of the photoelectric effect experiment, right? This idea of the energy of a photon related to its frequency, right? This idea of a photon being a chunk of energy. That's required from the photoelectric effect. The third one is probably the weirdest, but also the most important. And part of the reason it's weird is this statement sufficiently large. So this is the one that makes these models consistent, right? If you have a lot of photons, it looks just like a wave. You couldn't tell the difference. And so this is why you don't notice in everyday life light mattering whether you think of it as a wave or a photon, because as we'll see in a practice problem, any number of photons in everyday life is in fact sufficiently large. A quite large number. And so this is the thing that sort of helps us keep science consistent, even though we're coming up with these two seemingly contradictory models, right? So large number of photons, basically just a wave. Small number of photons behave in sort of odd ways. Okay, so a couple non-calculation practice ones here, right? Frequency, and we want to figure out things about wavelength and energy. So first thing we notice is that high frequency goes with high energy. That's E equals HF. So high energy, and so we eliminate A and C. And then we can use C equals lambda times F to relate the frequency and the wavelength, and those are inversely related, right? As frequency goes up, wavelength goes down. So the high frequency has to be a lower wavelength, that's D. These are really the two key equations. If you know those two, you're set. Okay. So here we have a total amount of energy and two different frequencies. We want to know which one has more photons per second, right? Watts is a joules per second, right? Joules per second. So if we know how much energy is in a single photon from the frequencies, we can calculate how many photons you need to get to the total amount of energy every second. And so the higher frequency has more energy per photon and therefore less photons. So the lower frequency will have more total photons. And that's this one, right? Kilo is 1,000, mega is 1,000,000. So kilohertz is less, right? So it should be the AM signal. Okay. Skipping this one, you'll see that in the second video. So the other thing that's important to note is because this photon model relates energy and frequency, the sort of energy conservation concepts that we can talk about for other problems now are really about sort of what light can interact with that in a certain way, right? So depending on its energy, in other words, depending on its frequency, different things can happen. And so this is kind of a good reference sort of set of values because like if I shine visible light on water, I can heat that water up a little bit. That's what this is. This is like heating. Right? And that's not a whole lot of energy. Visible light can do that. But it's still always just going to stay water. On the other hand, if I wanted to take that water and break it up into hydrogen and oxygen, that takes a lot more energy. It doesn't matter how much visible light I shine at it, I'm never going to be able to break the bond between atoms, right? A single photon of visible light does not have that energy. But gamma rays can, for example. And then similarly, like if I want to take those hydrogen atoms and get rid of the electrons, ionize them, that takes, once again, substantially more energy. And so I need very high energy gamma rays to be able to do that. And so understanding sort of the relationship between energy and frequency helps you understand sort of why things like gamma rays and X-rays are considered dangerous and visible light is not, even though you can have a very, very, very bright visible light and a relatively weak X-ray source, for example. So here's another non-calculation, right? We have photons of blue and photons of red. So the first thing we notice, they're both light. So same speed, right? We eliminate B and D. That was postulate number 1. But the blue light is higher frequency and is therefore shorter wavelength, right? So it's got to be that one. So brightness, that's really synonymous for intensity, and color is really synonymous with frequency, right? So the first thing is you have to do is recognize that. So if we increase the intensity without changing its frequency, right, we can't change the energy of each photon. That would require changing the frequency, right? B and D are the same, and both wrong. And similarly, E is really the same as well, right? Frequency, energy, and wavelength are all like, they all change together. If we don't change one, we can't change any of them. Speed, right? It's still light. That's postulate 1. They all get the same speed. So it's got to be A, right? Intensity is about a count of photons. All right, wavelength is double. What happens to energy? Well, doubling the wavelength must halve the frequency, and halving the frequency halves the energy. So it's got to be A. Skipping this one and that one. And I did that. So the important bit is to kind of extend our knowledge of this photon model to all the different types of electromagnetic spectrum of light. And this is really the important thing to keep in mind, is that both are true, but some ways are more useful than others to think about. And basically, the idea is the higher frequency, the more particle-like it is, and the lower frequency, the more wave-like it is. So this is a really handy picture to keep in mind, or I guess more diagram, right? The spectrum is organized by either wavelength or energy, right? Because we can think of it as either a photon or a wave. And things down here, right, those are waves, basically. They don't really have a whole lot of particle-like properties, but things up here basically behave like particles, right? If I want to explain what a gamma ray does and how it does what it does, I need to treat it like a photon. But if I want to describe how AM radio waves travel, that's not very useful. And so sort of knowing this is a really, really important thing to know. This would be a good slide to sort of save and review. Right? That kind of is what I said. And then, so this is another term that is handy, right? And I kind of already referred to it, right? Photons that have sufficient energy to ionize atoms or break bonds in molecules, those are referred to as ionizing radiation. That's basically X and gamma rays. Some ultraviolet, that's what we call a sunburn, but mainly X-rays and gamma rays. Those are dangerous, right? Because they have enough energy that they can affect the molecules in your body and therefore damage tissues and cells. And so if you ever see that phrase ionizing radiation, that's just basically telling you this is high energy and deadly, potentially. So really, right, this is the important message, right? When do we care? Well, two circumstances, really. The first is when the energy in a single photon is quite high, right, X-rays or gamma rays, or we don't have very many photons, right, a very, very, very dim light source. Okay, so now we're moving back to chapter 28 to add a little bit more depth with the quantum mechanics of this photon model and some of the odd results. And so this is probably the hardest to explain thing of the entire year so far, but it's really critical that we think about it very carefully. So what we want to do here is to say, okay, physics, I'm onto your little trick with this light being a wave and a particle thing, right? We saw with this double slit, right, the double slit diffraction or interference experiment, we saw interference. That's a wave property. But we also know from the previous slides that if we have a very dim light source, right, we then have to really care about things behaving like particles or photons, right? A dim, very dim, and by very dim, I mean like maybe we send out like 5 photons a second, which again, as we'll see in a practice problem, is an extremely dim light source. And so we say, okay, look, if light's a wave, then we're going to have to see interference, but particles can't interfere. So this much dimmer light source is going to force it not to interfere. So we'll figure out which one it really is, because if it interferes, it's got to be a wave. And if it doesn't interfere, it's got to be a particle, because particles can't interfere. And so we do this experiment, and something very interesting happens, right? So this might be like we let our light source be on for like 2 or 3 seconds, right? A very small number of photons travel out. Each photon hits our sort of collection surface somewhere, and wherever it hits, we get like a little beep sound. It says, okay, there's light right there. And we don't see any pattern at all. So like, oh, great, look at this, perfect. Light must be a particle. There's no interference there at all. So then we do it again. Now instead of maybe 5 seconds, we wait, 20 or 30 seconds. And that's like this image right here. A lot more photons. And now things start to get a little bit troubling, because it looks mostly random, like you would expect if there's no interference, but I can kind of see there's sort of a pattern right there and kind of another grouping right there that don't look like interference fringes, but they look like areas that are sort of more concentrated photon spots than anything else. And so that's a little bit troubling. So now let's wait, instead of maybe 10 or 20 seconds, let's wait for like a minute. And so we wait a minute, and that's this image. And now it's really troubling, because there's clearly places where the light is more likely to be than others. Clearly, right? I can see sort of the start of a fringe in these 3 spots. I can see that. It's obviously there. The light is not randomly scattered. There must be some sort of pattern to it. And then maybe instead of waiting for a minute or two, because now I really want to see what happens, I wait for like 10, 20 minutes, and I get this. And that looks identical to the interference fringes that we did in class with a very bright laser source that was, a wave interference description. So how did we get from this to that? The only way that image D can be produced the way that it is through interference. We calculated it. We showed it. If you didn't have interference, you would just have the light sort of smeared out evenly everywhere. But we don't have that. So we have to have interference. But this image up here, image A, you can count the photons. There's maybe 20 dots there. How do those 2 pictures remain consistent with each other? And this is, again, a very troubling question because it looks like we've hit a place where the models sort of contradict each other. This says very clearly light's a particle. This says very clearly light's a wave. And all we did is do the exact same thing for a different period of time. And it can't be both because particles don't interfere and waves don't go to single points. So we can actually make this worse too, right? Remember I said we did this, like maybe this is like 5 photons a second. What if we were really tricky and we come up with a light source that sends exactly 1 photon whenever we press a button? So like we press a button to turn it on, we get 1 photon that goes through our double slit experiment area and then nothing else. So we press the button again, we get another photon and so on. What if we do that and we press that button 1,000,000 times? If we do that, are we going to get to image D eventually? Are we going to get interference if I send a single photon at a time? And the answer to that is yes. Mysteriously and bizarrely, yes. If you send a single photon into a double slit experiment, one by one, by itself with nothing to interfere with, you somehow get interference patterns in the end as long as you have enough photons to see it. It's completely inexplicable with any sort of logical pattern of physics. But the conclusion that we have to draw is that the only way this works is if we can't really describe a particle or a wave as what light is either. It's somehow both simultaneously. What we call a particle has the ability to interfere, and what we call a wave has the ability to sort of be groups, individual bits of energy. There is no sort of word that describes that. Like the English language isn't suited to understand how light behaves under these circumstances, which makes it very hard to describe. And so the only way this works then is if the photon somehow, as it reaches the slits, interferes with itself, therefore there's something to interfere with, and then creates the wave-like pattern, then goes back to being a photon on the other side. Again, confusing only begins to describe this problem. But this right here, right, this explanation is the only way to make the experimental data sort of internally consistent. And that is real data. That is a real picture. I will say that this is a little bit of an incomplete picture. There are slightly better ways to explain this that are a little bit higher level for this class. And I'll talk a little bit about that depending on what kind of questions you have, but it's not quite as bad as it sounds, but it's pretty bizarre. So their conclusion here is, for this level, I would say accurate. But I think it's a better statement to say that what we call a particle can always behave a little bit like a wave, and what we call a wave can always behave a little bit like a particle. And we'll see more of that in the rest of this unit. It's not that sort of sometimes light is one and sometimes light is another. It's always both, and we don't always see the whole picture. Right? It's kind of like those optical illusion type things where if you look at it, sort of when you angle it to the left, you see one picture, and then you look at it the other way and you see another picture. They're both there the whole time, but you just don't see it under all the conditions. And we'll see more of that coming up. But I did want to throw this like one quote in. This is I guess more of a philosopher writing about sort of the views of physicists at the time. Because I mean, imagine this problem is that there were people that studied light and the wave properties of light with interference experiments and made their careers out of it, 30, 40, 50 years with light behaving as a wave. And then suddenly people show up and say, no, light's a particle. Here's an experiment that proves it. And so they go do their experiments again and it works perfectly like a wave. And then the physicists that find it's a particle do different experiments and they still show it's a particle. And these are contradictory things, right? Particles and waves are exclusive concepts in the ideas of classical physics. And so to try to sort of put those two together when you spent your entire life believing that they're completely opposite is kind of a scary idea. And so this is one of the main issues with quantum physics is that it forces these kind of contradictions to be resolved. And so the way physicists handled it at the time, of course, was quite bad. Mainly they just kind of ignored the other side when they didn't want to listen to it, more or less. But why is this kind of okay? Well, the first thing, right, again, we only would notice this at extremely low intensities. And so in everyday life, we don't notice this seeming contradiction at all, right? Postulate 3 really saves us. The fact that once we have a lot of photons, we could never tell they were individual photons, and it wouldn't matter whether it behaved like a wave or billions upon billions of photons. It would work the same. And so that's kind of the important thing to keep in mind. That resolves some of the problems here. So this question is one that perhaps looks either deceptively easy or deceptively hard, depending on what you think about it, right? Trajectory, right? What's the path it follows? Well, I mean, what are A and B saying, right? I don't even know, right? I know what light does. Light's a ray. It travels in straight lines. That's C. And sure enough, right, that's not really going to change, right? What light does sort of on the whole is not anything different. Yes, there might be an electric field oscillating, or maybe it's a photon traveling. It doesn't matter. The end result is light travels in a straight line. But again, I will say this is a little bit of an incomplete explanation, and light is a little bit more complicated than that. The end result is the same, right? We know experimentally that has to be the right result, but there's a little bit more to it than this describes. But for now, just we aren't redoing everything with light. All right, skipping that one, we'll come back to it. So you might have asked the question as I was describing that sort of double slit experiment, is that even possible? Like, how could you detect a single photon? Could you detect and emit single photons? Is that even possible to do? And the answer to that is yes. And really, it's a photoelectric effect concept, right? If you have a single photon that has enough energy to excite an electron, then all you have to do is be able to measure current very precisely. And if you measure current very precisely, then you know when a photon has arrived. It's either zero or not zero, and not zero tells you you've got a photon. And it is possible to make detectors for current that are that precise. So yes, you can detect single photons. Right, solar cells are examples of this, actually. Right, solar cells are basically photoelectric effect testers that are hooked up to a motor or a battery, depending. Right. Skipping this one because we'll come back. In addition to that, right, digital cameras and modern telescopes work this way too. You might have heard the term charge-coupled device, CCD. All telescopes are thousands upon thousands of CCDs, right? These pixels, each pixel is basically one of these CCDs that says, yes, I got a photon, or no, I didn't get a photon. And so from that, you can figure out sort of where the light is, and specifically as well, how much energy that electron has tells you what color the light was, right? So you can know the color and the brightness. And so CCDs are just, again, photoelectric effect things. So this is experimentally completely possible and not even rare anymore, although obviously extremely sensitive ones are quite expensive. So these next two questions are ones that I think are very important, because just because we're introducing light as a photon doesn't mean that we want to forget about the times it makes sense to describe light as a wave. The math we did talking about diffraction and interference is not wrong. It's just a little bit incomplete. You have to talk a little bit more about what the wave is, and that's something, again, we can get into a little bit more. But there are times where describing light as a wave makes sense because that's pretty much what it's doing. It's yes, there still might be a photon model underlying it, but the interference happens, and so why not just calculate like a wave and save yourself the trouble? And so sort of knowing what phenomena experimentally mean light is working like a wave versus what ones experimentally mean it's working like a particle is very important. So first thing, right? I notice photoelectric effect, that's a particle, that's out. Quantization of energy, right? We talked about that term. That's particle, that's out. B, we have not talked about yet. We will, but this idea of only certain wavelength, that's a quantization of energy concept too. And so that one's out. So C, the limited resolution, we talked a little bit about that, right? Diffraction, limiting resolution. And so that's the one that sort of deals with interference and diffraction concepts. So that's the one that's best to describe light as a wave for. And then similarly, right, now the opposite, right? Light is a particle. Well, we know A is out because that was the wave one. We see the word diffraction, that's a wave concept, that's out. These last two, right, photoelectric effect and quantization of energy are definitely particle concepts, but C deals with light, D does not deal with light, right? This is an actual particle. We'll talk more about what D means too. That's another chapter coming up. So these will be something that's more confident, hopefully described later. But right, photoelectric effect is light as a particle. D is actually a particle, so it should be C. Okay. And so the next part, if you just want to see sort of some practice calculations with these, that's the next video I'm going to do, so you can go to that just for the practice problems. But these are helping describe the concepts. So that's it for this section here.